If you don't recognize these 7 integrals instantly, you could be losing easy marks in 9709 paper 3. The first integral is integral of sin²x dx. Okay, so the mistake here is to try and do a direct integration, but we don't have a formula for sin²x, and so we use an identity. So the identity we use is cos²x is equal to 1 minus 2 sin²x. This identity is available in your MF19 formula sheet. Making sin²x the subject, we get 1 minus cos²x by 2. We can actually just split it up into two terms, half and negative cos²x by 2. Now we substitute this into the integral. So instead of integral sin²x, it is going to be integral of half dx minus integral of cos²x by 2 dx. These are easy integrals. All you have to do is half dx becomes half of x, and cos²x becomes sin²x by 2, and the original 2 remains as well. Let's see. A similar integral would be the integral of cos²x dx. Again, we use the identity cos²x is equal to 2 cos²x minus 1. Make cos²x the subject, so it becomes cos²x plus 1 by 2. And then you substitute this into the cos²x integral. The second one is the integral of tan²x. Again, the tendency is to just do a direct integration, but you cannot do that. There is no formula for tan²x. So what do? Use another identity. And which is that identity? 1 plus tan²x is equal to sec²x. Make tan² the subject. Tan²x is equal to sec²x minus 1, and substitute this into your integral. So you have integral of sec² dx minus integral of 1 dx. Remember, this is available to us in the MF19 formula sheet. You just have to remember that there is a connection between tan²x and sec²x. There is an identity available, and then go look for it in MF19. So this now becomes a simple integration. You just have to use the formulas from your formula sheet. So integral of sec²x is tan×x, and the integral of 1 is x plus c. The third one is the integral of tan×x with respect to x. Here, what you want to do is replace tan×x with sin×x by cos×x. This, you have to recognize tan×x and make the substitution yourself, because in the paper, they're not going to give you a hint as to how to carry this out. So once you have sin×x by cos×x, so usually in any integral that has a sin×x and a cos×x, either both in the numerator or numerator denominator, it's usually a substitution question. So we're going to substitute the denominator. U is equal to cos×x, differentiated. So du by dx is a negative sin×x, right? We have a sin×x dx here. So sin×x dx is negative du. And now we're going to substitute u and the sin×x dx into this. So integral of sin×x dx is negative du, and cos×x is u. Once again, it's become a simple integration. So it becomes negative log u plus c, and then we substitute the u value back into this. So it becomes log of cos x plus c. They may ask you to integrate log x. Now, no hints will be given to you. So this is an integration there whose method you must remember. And it is a integration by parts. The method that we use is integration by parts. So how does that work? You first write this down as log x into 1 dx. Right? So we're going to take log x as u and 1 as v dash. So u is equal to log x, v dash is equal to 1. We're going to integrate u to get u dash, which is 1 by x. We're going to differentiate v dash to get v, which will be x. And then apply the formula for integration by parts, which is uv minus integral of v u dash dx. Okay, so substituting all the elements here, u is log x and v is x. I'm just putting it in front of log x minus integral of v is x, u dash is 1 by x dx. So I'm simplifying this by cancelling out the x's. So I have x log x minus integral of dx, which is x log x minus the integral of 1, basically this is 1, is just x plus c. Right? So remember that if you're doing an integral of just plain log x, we are going to use integration by parts, and you're going to initially write it out as log x into 1 and then assign u and v dash to both the functions. The integral that you need to recognize is of the form integral of 1 over x squared plus a squared dx. Okay, this one integrates to give us, this is there in your formula sheet, your MF19. This gives us 1 by a tan inverse of x by a. Right? But the crux of this is that students often don't recognize this because it doesn't look exactly like x squared plus a squared in the denominator. So the thing that they forget to do is remove the coefficient of x squared. So in order for this formula to work, x squared can't have a coefficient. So what do? We manipulate the equation. So 1 by, remove the 2 because x squared can't have coefficient. Open a bracket, so it becomes x squared plus 5 by 2 dx. Right? And then you take the half out of the integral sign. So half integral of 1 by x squared plus 5 by 2 dx. Now if I wanted to write it so that it looks like this standard form here, I can write it as, this is so that we can identify the a. I can write it as integral of 1 over x squared plus, the 5 by 2 is a squared term. So we can write it as root 5 by root 2 the whole squared dx. Right? So what we have here is a is root of 5 by 2. And now we can apply the formula. So keeping half intact, 1 by a would be 1 by root of 5 by 2 tan inverse of x by root of 5 by 2 plus c. So the fifth integral is works out to be a tan inverse integral, but you need to be able to recognize this. So how do you recognize it? There is an x squared term and there is a constant and there is a plus in between. So that's how you recognize it. And the key to doing the whole thing is to ensure that the x squared term does not have a coefficient. The integral you need to be familiar with is the integral of sin³ x dx. So this is an odd power of sine, and the same method would work for an odd power of cos as well. So what you need to do here is replace the sin³x with sin²x into sin⁡x dx. And then we'll replace the sin²x with 1 minus cos²x into sin⁡x dx. Okay, after this, there are a couple of different ways to solve this. But since it is a sine and a cos expression multiplied into each other, I would just go with substitution. So substitute u is equal to cos x. So du, remember with substitutions, right after you make the substitution, you have to differentiate it. So du by dx is negative sin x, and sin x dx is negative du. So substituting the u and this expression here, sin x dx, in our original equation, we get integral of 1 minus u squared, and sin x dx is, I'm putting the negative sign outside, negative du. Okay, this is now a pretty simple integration. So it's going to be negative 1 integrates to become u, and u squared integrates to become u cubed by 3 plus c. And then we replace the u with cos x. So negative cos x plus cos cubed x by 3 plus c. The final integral that you must recognize is the integral of tan inverse x. This, like the log x, is a integration by parts question. And we know that for integration by parts, you need two functions multiplied in the numerator. So in this case, there's only one. So we're going to multiply it by 1 dx. And then make a substitution. Tan inverse x is u, and 1 is v dash. So if u is tan inverse of x and v dash is 1, then the differential of tan inverse x is 1 over 1 plus x squared, and the integral of v dash is just x. The formula for integration by parts is uv minus integral of v u dash dx. So u into v is going to be x tan inverse x minus integral of x over 1 plus x squared dx. Right. Now, what do we do with this integral here? This is a perfect example of integration by substitution. So, we're going to substitute 1 plus x squared is equal to u, and du by dx is 2x. We have an x dx here that needs to be substituted. So x dx according to this is du by 2. Right. So x tan inverse x minus, I'm making the substitution now, x dx is du by 2, and 1 plus x squared is u. So going to carry that out. X tan inverse x minus, I'm bringing the half out and I'm integrating 1 by u. So 1 by u's integral is log u. And then I'm adding the plus c. So that gives us x tan inverse x minus half. I'm substituting I'm substituting u with 1 plus x squared. And plus c. You can see none of these are difficult, but if you don't recognize them, you lose marks instantly.